Hi, this is continuation for Power Electronics lectures, and today we are going to continue our talk about buck converter design. And today we have power converter considerations. In the previous video, we have seen the analysis of buck converter, the relations, and also some examples. And today we are going just to consider some other things that might beginner designers they ignore at the beginning. So what we have in this circuit, we have some components and circuits like high side driver here. We talked about high side driver and why we need it for that switch. We have spoken before about power losses and how we calculated for a switch and diodes. And we consider speaking about thermal design and how to choose a heatsink and thermal resistance. And also we spoken about the reverse recovery time for the diode. All that have been covered before in the previous videos. But today I'm going just to expand the talk to consider something related to the inductor and the capacitor. And I think when I mean the inductor, I mean the inductor saturation. What we mean by the inductor saturation and why it's very important and might fail your buck converter if it's not considered well. And also the inductor ESR. ESR means the equivalent series resistance. So every component has still some very small resistance in series or in parallel. It depends on the component. And yeah, we have here inductor ESR. Does it mean something for us? The same for the capacitor. We have something called capacitor ESR, equivalent series resistance, and capacitor ESL, equivalent series inductance. Okay, so that one has some inductance and some resistance. Is it important to look at these? Will that change the waveforms of the output voltage or output current? These are the questions that we want to reveal in this lecture. And all that also will contribute to something called noise or electromagnetic interference. And this might fail your circuit if you are going to commercialize it. So that if the noise is very high and maybe above the standard threshold, so you can't do that and you will not be approved. Okay, so the talk about this will be just combined with the talk about all other parameters. So what we mean by inductor saturation, we know we can design the inductor by a value. So we can say that we want 0.6 millihenry or 1 millihenry for our buck converter. But when we look at the market, we have variety of shapes and types of that inductor value. We might see something like this, small one, yeah, maintain the same current, and that one has different shape, that one has different core, this one has a black core, this one has a yellow core. Is that really different from one core to another core, or that one? So we have two categories of inductors used for buck converter. The first one is called the Bowder inductor, the Bowder core inductor. And when I talk about the inductors here, I talk about cored inductor. Maybe it has a Ferrite-core inductor or Bowder core power inductors. Okay, so when we look at the power inductors and we select, for example, 15 microhenry power inductor, we can see that the value is not constant when I run it in a circuit consuming that output current, okay, or delivering that output current. So we have the output current, maybe if it's very small here, okay, within 1 ampere. So we still have the 15 microhenry here, okay. So the inductance here will start to drop if I increase more current. And that's very important thing that you need to consider in your design, that if you have an inductance and you want to select one from the market, you have to look at what is the value of your output current and how much drop you have in your inductor inductance. Okay, so in Bowder or iron core, because the Bowder it means iron, okay, inductor, the dynamic inductance decreases almost linearly while the current increases, and you have seen that from here. Okay, but the other choice is the ferrite. And when you look at the ferrite here, yeah, we have many examples. The first one is 680 microhenry, and yeah, we see here this is the logarithmic scale, so the scale will be different. Okay, so we have 680 microhenry here, okay, and yeah, it drops and then it dramatically or significantly drops here, okay, to a very small value, maybe 1000 less, okay? And we have here the same for 220, 100. So it maintains the same inductance, which is very good for low current performance, okay, within 1 ampere for the last one here, okay? But when you increase your current delivered to the output, that will affect your inductance value and it will drop. That's because the inductor core saturation. So you are saturating your core, and that doesn't actually give the same flux all the time. So in Ferrite-core inductors, the dynamic inductance is non-linearly decreasing while the current increases. So what we mean by saturation, we mean this regions here, okay, where we have high current and very high significant drop in inductance, okay? Maybe that doesn't appear here. That means the powder inductor has a very high saturation current. So to saturate that power inductor, maybe we want to deliver 10 ampere, for example. But that one, for example, the lower one here, we have just a 3 ampere and it will be saturated, and we can't actually rely on it. The saturation of the inductor means we are converting our inductor to a short circuit. This is one easy way to understand it. So we have our buck converter here, and we have two inductors, the ferrite and powder iron inductor. So in the lower current delivery here, okay, 0.15 ampere, I think both of them, they still okay, and they drop very slightly and still linearly, okay? But when you look at the very high current delivery here, we have seen now the inductor, the powder inductor, yeah, the drop is a little bit smaller than the drop of the ferrite, where the ferrite is going very fastly to be very minimum inductance compared with the nominal one here, okay? So now what will happen to the waveform of the inductor? And the iron or the ferrite, they still keeping the same shape here nearly, and we don't have any problem. The saturation is still not appearing because still we maintain the same inductance for the same current here. And this explanation is just for you to read if you want to add more notes. But what will happen if I increase the current delivery to 2.5 ampere? We look at the inductor from the powder iron here, but still we have nearly very linear drop here. But for the ferrite, it's very high drop, significant drop. What will happen to the inductor current waveform? It will spike, because what I mentioned, the inductor saturation look like a short circuit. So you are short circuit your inductor, okay? So what will happen? The voltage will spike very high. So the red one here is for the powder iron, okay? But for the blue one here is for the ferrite, which is saturated by the high current. And this is what happens, very high spikes. What will happen if we have these spikes? That will affect the current going through the switch, and that spikes might damage it, or through the diode, and also that might damage it. So these things here are very important to consider in your design. So these are two waveforms. For the first one on the right, there is no saturation, and it's powder inductor. And here the waveform of the inductor is very normal. But look at the ferrite inductor. When we deliver 1.9 ampere, that means it's saturated, and we have seen here very nonlinear di by dt, and also a high value, high rise for the current here, and that will spike and then will go like this. So that shape, if you see it on your oscilloscope for the current of the inductor current, so that means you are saturating your inductor, and that might affect sometimes the output waveform, but it depends on the circuit and the output load and the inductance as well. So the ferrite inductor are not used in deep saturation, so we might go for a little bit of saturation, but not deeply, because that will rise very highly and that might damage your switches. A moderate saturation can be allowed in high power density supplies design, where small core size parts are needed. So why we need sometimes to go for ferrite if it saturates very easily on at high current? Because they are smaller size. That's the benefit of ferrite inductors. Powder inductors are bigger and more dissipative than ferrite ones. So the ferrite one is better for size and for performance and also for high frequency, because powder lose power and also dissipate more heat if I turn it or switch it very high frequency. So that's why sometimes designers look at what is better for their application. If it's low current delivery, that means we can go to the ferrite inductor. If it's very high frequency, also we can choose the ferrite inductor. But for high power and also high frequency or medium frequency, we are going to use powder inductors. So the other thing we want to look at for the inductor is the ESR. The ESR is the resistance of that inductor, and I think what concerns us is the dissipation of the heat of that inductor caused by the resistance. So we are looking always to very minimum resistance ESR for the inductor, because the power dissipation is calculated as I square RMS multiplied by that resistance. So if that resistance is very small, so the power dissipation and the heat dissipated by the inductor will be minimum. So now let's go to the capacitor. Capacitor ESR and ESL. We have that capacitor here. What concerns us if it has capacitance, resistance, and inductance? So the model of the capacitor, always they model it like this. We have a series inductance, and that series inductance caused by the leads of the capacitance, because we have some leads and also the plates inside that capacitor. And the ESR, we have some resistance caused by maybe the dielectric or also the leads and the metal inside the capacitors. Okay, so this is the normal or popular model for the non-ideal capacitors. So okay, what concerns us if we have ESR or ESL? By looking at the waveform of the inductor current, we have that inductor current like this. So the current going through that inductor will look like this. Okay, what will happen to the capacitor voltage here? Looking at the capacitor voltage, okay, we will start seeing some steps like this and some jumps and some linear relation. The ideal case for the voltage of that capacitor is like very minimum variation, which is delta V output, and it look like a sinusoidal waveform. Okay, so we are looking here for very minimum sinusoidal waveform because it smooth that waveform, and we should see something like this. Okay, but this is not appearing here. Why? Because we have ESL and ESR. Now, why now there is some steps here if we have ESL? Because we know that ESL or the inductance in general doesn't allow change in current. And now at this point here, we are changing the current. And that change in current also will go through that capacitor, and that will produce a jump in the voltage. And that jump is calculated as LdI by dt, and that's the delta voltage across the inductance. That's parasitic inductance. So this is something that concerns us, because if it's very large, that means it emits some noise, and that might reduce the quality of your design. Okay, but what is the effect of ESR? As I mentioned, we are looking for very smooth voltage. If we have that current, very smooth voltage like that. Okay, but that current, okay, that voltage here means that we are copying the current, and I think the component that copies the current to the voltage is the resistance, because the resistor equals linear relation between the voltage and current. So if I have that current, okay, will pass it through that capacitor, I mean the rebel one, okay, that will produce the same shape for the voltage. But the ideal one, it should be very exponential, like sinusoidal one, exponential decrease or increase for the voltage. So that's why we have some concerns about the inductance and resistance of any capacitor. The other thing is the variation of the ESR with the temperature. So a real ESR changes with the temperature and with the frequency, and this is also something that we have to consider. So the ESR here, sometimes it might be increased or decreased with the temperature. So this is one of the examples okay, of the current value. Here the current, okay, the inductor current, and also the capacitor voltage, okay. So the capacitor voltage is like a copy of the inductor current, and that means I have very high ESR resistance, okay. So it's like a copy of the inductor. We have a smooth here. Look at this. We have exponential a decrease of that capacitor. That means we have in ESR, but that ESR is not very big, okay. We have a jump here. That jump is called by ESL, and this information are not actually from books. It's from the references from manufacturer application notes. And as it mentions here, the output current is 0.5 ampere, but we have a resistance value for the capacitor. It doesn't mention the inductance value, but I think we can see it from this portion here. And by looking over the internet, I have found an example from a manufacturer for some capacitors and buck converters, and they designed a buck converter to supply 5 volt, and they put at the output some different capacitors, but the same value, nearly the same value. So in the first one here, they have put aluminum capacitors, and that aluminum capacitor has a value of 47 microfarad, and the ESR, the resistance, is 421 milliohm. Okay, you might say 421 milliohm is very tiny, but this is the expectation for ESR or parasitic components, okay? So now by looking at the voltage variation across that capacitor, they have got this waveform, and I think this waveform means it's a copy of the inductor waveform, inductor current. That means we have very high ESR, and yes, it's very high ESR here. And the variation, because of that, is 220 millivolt. So if you have 5 volt here output, your 5 volt here will go to 5.2 and 4.8, 5.2 and 4.8, which is considered as low quality design. But they replaced this aluminum capacitors, which featured as high ESR, by another one polymer capacitor, 47 polymer capacitor, in parallel with 4.7 MLCC, which is multi-layer ceramic capacitor. That's called ceramic capacitor. And the polymer capacitor has ESR of 20.7 milliohm. So look at that. It's very lower compared with the first condition here, or first state. So what is the voltage variation? Look at that. It's very nice exponential growth for the capacitive voltage here and there. We have some notches there, and that's because of the switching and some capacitive components, parasitic capacitive components in the PCB itself, but it doesn't mean that we have resistive or ESR impact here. So there is no ESR impact on this buck converter because it doesn't actually copy what's happening here. We have some notches there and notches there. That might be of the inductance of that capacitor, or might be from the design of the buck converter and the PCB inductance itself and the Triacs inductance itself, okay? So we have very nice variation here, and the variation is about 20 millivolt. So your 5 volt will just jump within 20 millivolt up and down. And I think that one is 220 millivolt from peak to peak. That means it will change from 4.9 to 5.1. Now, the last one is 2 ceramic capacitors in parallel together, okay? And that will bring the ESR to 3 milliohm. And yeah, we see here very exponential growth for the voltage there and there, but very high spike here and there. Why? Because the MLCC has very low ESR, but also has a significant value of ESL, which is the inductance. But that one is better than this one. So the manufacturer recommended actually this design, which is polymer capacitor in parallel with MLCC. They will provide low ESL and also low ESR. And actually the value of ESR and ESL doesn't impact the waveform or the variation of that voltage. It also impacts the transient. So we have here a variation of the ampere from low to higher one, and that gives the voltage output here some different waveforms. So we have this spike here is caused by ESL, and that one is caused by ESR, and this one is called by the inductance value. Okay, and we have another slide here just showing the same thing. Output current changes, and we have here jump in the voltage because of ESL. We have here a linear relation or ramp because of ESR, and we have here very exponential one because of ESL. So if we have very large capacitance value, that means that transient will take longer time than smaller one. If we have ESL bigger and bigger and bigger and bigger, that means ESL4 is bigger than all these ESLs. That means it will produce very high spike here. And the same for the ESR. If it's bigger here, that means very high drop here for the voltage during the transient. And this is very important. This slide sometimes summarizes what we have spoken about. We have unsaturated inductor. The inductor waveform will look like this. We have saturated inductor. The inductor waveform, current waveform will look like this, spiky one. If we have high ESR, the waveform of the voltage will look like the same as the current. But if we have low ESR, it will look like sinusoidal or very exponential one. The last one I want to speak about is the snubber circuit. What is the snubber and why we need it? It provides protection by lowering the stress on switches. What I mean by stress, the high voltage and the highest voltage and the highest current applied or flowing through that switch. It provides also protection by limiting the rise rate of the current or voltage, and that limits the EMI, which is very important. When you have ESR or ESL, as we seen previously, that current also will go through the switch, and the switching also will be very hard, and that will produce spikes, and that spikes also can be emitting some magnetic interference, and this will reduce your design quality. And also it provides switching losses reduction, so efficiency will improve. So how the snubber circuit look like? I have chosen just one snubber circuit because we have different snubber circuits in the literature, but I just one a popular one, which is this one. So we have an inductor, we have a resistor, and we have capacitor here. So how this snubber circuit, which is across the switch, will help to protect and to reduce the switching losses? I think if we have inductive load here, that inductive load, once I switch off that transistor, that inductive load will try to push that current to that node here, but because that is off, it will try to rise the voltage until this switch on, and then that will consume the current or will flow the current. But at that moment exactly, the voltage here has a little bit of risk on that switch. Okay, so that's why they made another track for that voltage or current to go and to charge a capacitor here. So that capacitor will be charged during the turn off condition. That's why they call this snubber circuit the turn off snubber circuit, and that they will make the charging for all that spikes and that energy into that capacitor. Okay, and that also will maintain some capacitor voltage across the switch during the switch off and will limit that. So if we have very high spike here, that will be absorbed by the capacitor and that spike will be reduced. That's why we said it's lowering the stress and protecting it from damaging. And also it will limit the rise rate. Why? Because the capacitor charge that current exponentially, so it will be very low rate compared with the case without the capacitor. So this is the case without snubber circuit, and this is the case with the snubber circuit. So the voltage, okay, across that switch will be slowly increasing like that, okay, during the turn off. So the current now will reduce, okay, but that voltage across that switch will not rise significantly or very fastly. It will rise slowly or exponentially according to the charge of that or the capacitance value here, okay, and that will limit the switching losses as we see here compared with the previous one. We can increase also the capacitance value, and that also will make the rise of the voltage across that switch very slowly, and this also will reduce it more and more. But the problem with that is when I turn on my switch here, okay, that means I have to discharge this capacitor through that that resistor. And now the energy stored during the turning off of that switch will now be delivered or dissipated by the switch itself. So that's why we have a trade-off. If you want to increase the capacitor to reduce the switching losses, this also will increase the turn-on switching losses, because all that energy will be flowing through that in that switch again when you turn it on. So there is just compromising between the capacitance and the switching losses. And this graph here is producing some relation between what is the optimum value for the snubber capacitance, just to make the losses as minimum. So we have, we are reducing the losses here, okay, to a minimum value when we increase the capacitance, okay, we increase here the capacitance, but if we still increasing the capacitance more and more and more, this will reflect back, and the switching losses will be higher and higher and higher. So that's why we have to be careful in choosing the capacitance value. The other point need to be considered during the design of the snubber. We know that the MOSFETs here, or the switches, have some leads, and that sometimes they are long, and you have PCB tracks, they are also sometimes long. They produce some parasitic inductance. And if you already have your MOSFET, and that MOSFET, we know that it has some capacitance here, that capacitance with that inductance will produce some resonance, okay? And that resonance will be like this, okay? So the F, the frequency of that resonance, is a function of the CP1 here, and also the inductance, the parasitic inductance, which sometimes we can't measure. Okay, so how that snubber will help to damp or reduce that spikes? It by changing making another track for the current, and that will dissipate the energy during the resonating of that inductance and that capacitor. And this now shows to us how the resonance, okay, happen at that point without any snubber, and with the snubber it will be damped and reduce the spike as well, or the overshoot of that, and will protect our MOSFET. And now if we are looking to some equations as a guidance for our snubber circuit, we have here the buck converter, and I just attached the snubber circuit across my MOSFET. Also, I want to say that the snubber circuit is not designed for just MOSFETs. You can really put some capacitor and resistor across the diodes as well. You don't need another diode, but you need at least resistance and also capacitive component across that diode, because this will reduce the EMI and also the spikes. So if I want to choose R and C, what is the approach for that? I have these two equations just as a guide for you. So the snubber capacitance equals I output times TF divided by 2 VF. What is TF and what is VF? The TF and VF is parameters that you need to choose as a designer, and they are the time you are looking for, okay, when your current is going to 0 and meet the 0 point here, and that time will correspond to the voltage across that capacitor or that switch as well, okay, during the falling of that current. So for example, if I choose as a designer, I want this point to be 1 volt when the current meets the 0 point. That means all that voltage from 0 here to 1 volt here will be very small if I multiply it by a current while it's falling, okay? That means I will maintain very low switching losses, okay? But choosing that to be 1 volt, that means I have to provide very high capacitance here to charge very slowly and maintain 1 volt here, okay? And later on will complete the charging for the capacitor, okay? So this one and that one is chosen by you, okay? And it might be here 1 volt or 2 volt, or sometimes the same as VC, okay? Sometimes 10%, 20% of the full voltage of off voltage. So the VF here definition is the desired capacitor or IGBT voltage when the IGBT current reaches 0. And we have for the resistance another equation which should be less than the T on divided by 5 CS. What is the T on here? The T on is the conduction time. We know that we turn the switch on and off, and the conduction time is delta T, or when we turn it on and we wait until the off time comes. So the on time here is not the switching on time. No, it's the on time for the switch itself coming from the PWM. So we choose it as this because we want the capacitor to finish discharging during the conduction time. Here we said that during the conduction time, okay, that capacitor now will still discharging the charge by the switch, okay, and we want that process or that operation to happen very quickly, the discharging process. So that's why we choosing it to be 5 times less, or 1/5 of the T on. And now let's have an example as a finish for this topic. The step-down converter here has the following specification are given below, and these are the given. We have V input as 200 volt, I output as 10 ampere, the duty cycle is 50%, the frequency is 100 kilohertz, and also the T off equals 0.5 microsecond. The T off means the switching of time, okay? So we want to design a turn-off snubber circuit during the criterion that the IGBT voltage, which is this one, the IGBT voltage reaches its maximum or final value, which is this point here, at the same time that the IGBT current reaches 0. So that point should be exactly when the current reaches 0, okay? So we'll see something like this. So that Tx will be the same as Tf here, okay? And we'll see something like this. That means the voltage will charge the snubber capacitor very quickly, okay? To the point that the voltage will be maximum or final value once the current will reach 0. This is not very good design. So now we will recall the equations for the CS and RS. And I think for the CS, we have I output as 10 ampere, and we have TF and VF. What is TF here? We know the turn off for the switching turn off is 0.5, okay? That means the TF here will be 0.5 exactly. We can choose 10%, 20% of that 0.5, but it says here we have to be the same, okay? So the turn off is 0.5 microsecond, and the VF, when the current is 0, it says the VF will be at final value or the off time voltage, and it will be 200, because when we switch off the Mosfet, it will maintain 200 voltage across its terminals. So that's why we have 10 times 0.5 microsecond divided by 2 times 200, and that will give us this value, which is 0.125 microfarad. Now let's go to the resistance, and I think we know that the turn on is the conduction time, and we know that we have a duty cycle of 0.5, and we know the frequency. I think from the frequency we can calculate the duration, which is 10 microsecond, 1 divided by 100 kilo, and also the duty cycle. By knowing that, we can calculate the turn on, which is 5 microsecond. Now by looking at this equation, we can calculate the RS as 80 ohm. So 80 ohms, and that capacitor value will make this losses here, okay? Might be this losses, it will be larger because we have a faster charge for the capacitor, and that means higher value for the voltage during the transition. So that brings me to the end of this lecture. I hope you gathered good information about buck converter design, equations, and waveforms. And in the coming videos, we will cover more topologies and more converters like boost converter, buck boost converters. But the discussion will be very fast compared with this one because we already covered more details about that one. Will be common also with the other converters. So thank you very much, and see you in the coming videos.